This is lecture 6, Chem 223. In this lecture, we will be talking about titration vocabulary and solubility constants. For this lecture, what I typically do in my in-person class is I give out a handout, and I will show you that handout right now. The handout just looks like this, and on the first page of the handout is just a bunch of titration vocabulary words. We will be going through these vocabulary words, and what I want you to do is print out this handout. So the handout is a total of 6 pages. You can print it on both sides, so front and back. Then I'd like you to follow along and fill out this first page with me as I go through the vocabulary words on the lecture slides. On the second page of this handout are some example problems, which I will go through in the lecture today that I would like you to follow along with. And everything on this page is already filled out with the material on the lecture slides, so it's free, or you can feel free to just watch the video at that point. And then after that, there will be 3 practice problems for you to work it through on your own. Completing this handout is a part of your quiz for this lecture, so make sure that you do it. And we will be having a few lectures like this where you get a handout. We'll have a very brief lecture, and then the rest of your work will be filling this out. At the bottom of this handout are the answers for the handout. I would strongly encourage you to work through the problems before looking at the answers, because what will often happen is you will look just at the answer and think, oh yeah, that makes sense, I can do that. But then when you have to work out a problem on your own without an answer, you have no clue how to do it. So I strongly encourage you to try and work through the problems, fail a few times, and then look at the answer, and that's how you'll actually learn things. As far as the vocab up here, I would also strongly encourage you to write these down as I go over them in the lecture slides. Writing them down and thinking about them is your learning activity that will help you remember them further down the road. All right, let me switch back to the lecture now. Okay, and I'm going to go through these. If you need to pause at the end of each word to give yourself a little more extra time to write down the vocab meaning, that is perfectly fine and probably what I would do in this lecture. All right, so the first word we're going to start with is titration. So a titration is an analytical technique for determining unknown concentrations of acids, bases, or other chemicals. Now, a reagent of known concentration is added to another reagent which has an unknown concentration. And you carry this out until you see some sort of change in your solution. The next term is your analyte. So your analyte is your unknown compound. So it's the species that you want to learn the concentration of. And then you have your titrant. Your titrant is your species that you have, or that has a known concentration. You're going to be comparing the volume of your titrant to figure out the concentration of your analyte. Now I will ask you a little quiz right here. When you're doing a titration, you have a burette, you have a beaker down at the bottom. Does the analyte go in the beaker or in the burette? All right, so a lot of you probably thought of an answer and thought that you had an answer, but I'm guessing that most of you are actually wrong. It actually doesn't matter if the analyte is in the beaker or if the analyte is in the burette. It can be in either one. As long as you know the concentration and volume of your titrant, then you're good to go. The analyte can be in the burette, where you drop it down until you reach some volume of analyte that causes the titrant to react, or vice versa. Okay, the next one is the equivalence point. The equivalence point is the point during your titration that you've added enough analyte that you have a stoichiometric amount of both titrant and analyte present in your solution. So the reason I don't say that you have the same amount of titrant and analyte in your solution is because let's say that your titrant and analyte react at a 1:2 ratio or at a 2:3 ratio or some other ratio. So what you want is a stoichiometric ratio where all of your titrant and all of your analyte have reacted with each other. And sometimes that's a 1-to-1 ratio, but oftentimes it's not. The indicator is the chemical compound that changes color depending on the pH or chemical stoichiometry of a solution. So most of the time when we think of these types of experiments, we think we're always dealing with acids, but we have one experiment that we'll be going over where we're titrating for iodine concentration. And so in that case, we aren't using a pH indicator, but we're using a starch indicator. And there's various other titrations that you can do. You can titrate for metal concentration or for specific ions or aqueous species in your solutions. The indicators are often an acid or a base, especially when you're doing a acid-base titration, but it can really be anything that changes color at a certain stoichiometric point. The indicator is added to any analyte solution to give the person performing the titration a signal of when to stop. The end point is related to the indicator in that the end point is where the indicator changes color and the titration is ended. So a question I have for you is the end point and equivalence point the same thing? The answer is usually not. So especially for a pH titration or an acid-base titration, you'll often use up all your acid or base before the solution starts changing pH drastically. And so it often doesn't reach your endpoint where your indicator changes color until a few mils after you've reached your equivalence point. So the difference between your equivalence point and your endpoint is what we call your titration error. So that is how much you are off in your titration. So the way that you determine your titration error is with what we call a blank titration. So in a blank titration, the titration error is discovered by titrating a solution without the analyte present. So usually that's just water and indicator, unless you have other species in there. So let's say you're trying to figure out your concentration of acetic acid in salt water, then you would just use blank salt water or a sample that's built to look a lot like salt water. And then the amount of titrant needed to change the indicator color is then subtracted from subsequent titrations. So the amount of solution that you need to, or the amount of titrant you need to use to get your indicator to change color in your blank titration, that volume is then subtracted from the volume that you use for your other titrations. That's known as your titration error. So you're correcting for it. The next word that we're going to cover is a primary standard. So primary standards are standards that we know the concentration of really well. And they are generally what we use to calculate the concentrations of everything else in our samples or in our titration. So the criteria for being a primary standard is, first, your standard has to be greater than 99.9% pure. If you look on most chemical bottles, they will list a purity for your sample. And those range from 50% pure or 20% pure. There's really no limit on the low end except for it has to be greater than 0%. But on the high end, these go up to 99.9% pure or 99.99. The more nines or the more decimal places you have, the more expensive that's going to be, the more difficult and the more purification steps you're going to have to go through. The second criteria for something to be a primary standard is it has to be stable, meaning that it doesn't decompose over time or when heated. So if you're going to leave this on a shelf for a long time, you want it to be the same stuff as what it was when you bought it, right? So milk isn't going to work because milk curdles after a while, but vinegar can work, although vinegar is not 99.9% pure, but it is stable for a very long time. The next criteria is it can't be hygroscopic. That means is it can't absorb water from the air. So several species do this. Several iron salts, for example, if you buy an iron salt, I believe iron nitrate is really bad at this. You buy iron nitrate, it'll absorb water from the air and it'll turn to mush over time. So anything that is a desiccant that absorbs water from the air can't count as a primary standard. All right, so there are three criteria for having a primary standard. Make sure you know what those are. The next term that we'll cover is standardize or standardizing. So solutions that have been titrated with a primary standard solution are considered standardized, meaning we now know their concentration really well because we've compared their concentration to that of a primary standard. Now, how long a standardized solution stays standardized depends on the solution. If it's something that decomposes quickly, then it's not going to be standardized for long. If it's something that's stable for a long time, then it can be standardized for a long time. Then the last term we'll cover is stock solution. This is a solution which is already prepared and is available for use. So that covers everything on the titration techniques and vocabulary. We're now going to switch gears to solubility constants. Now, hopefully you remember something about solubility constants, but if not, I'm going to discuss them and review them now. I've also opened a discussion under Digital Dialogue on Learning Suite about KSPs and common ion effects, which we'll cover on the next slide. So if you feel like you're struggling with this and need help, you can either turn to me or turn to other classmates to ask questions. I encourage you guys to participate in those discussions and throw out questions either through Digital Dialogue or just through emails through Learning Suite and ask each other for help. I can always answer your questions, but I feel like you'll get a better learning experience if you engage with each other and try and help one another. All right, so let's go over this problem though. This question is, an instructor is teaching a lecture and has a 1 liter bottle full of drinking water. So this is just sitting on the desk or counter in front of him or her. At the beginning of the lecture, a small piece of chalk, which primarily consists of calcium carbonate, lands in the drinking water. So chalk has a KSP or solubility constant of 3.36 times 10 to the minus 9. And this calcium carbonate's now in our drinking water. And the question is, if the instructor drinks all the water, is the dose of calcium that that instructor ingested more or less than they'd ingest from a Centrum vitamin, which contains 210 milligrams of calcium. All right, so the first thing we need to do in this problem is write out the chemical equation of the reaction that's happening. So we have calcium carbonate, and that is dissolving into the calcium 2+ ion and the CO3 2- ion. These species, of course, are both aqueous, and the calcium carbonate is solid. The next thing we want to do is write out our KSP equation in terms of our products and reactants. All K values in chemistry, at least all capital K values, are products over reactants. But with KSPs, we get the special benefit that all of our reactants are always solid. And so our KSP then is always just equal to the concentrations of our reactants multiplied together. So what we're looking for is figuring out the equilibrium concentrations of the calcium and carbonate ions. And we set that equal to KSP, which we know from our question has a value of 3.36 times 10 to the negative 9. The next thing we need to do is set up an ICE table. So if you don't remember what an ICE table is, an ICE table stands for initial change in equilibrium. So we need to figure out the initial concentrations of all these species in our drinking water. So we're going to assume that there is 0 calcium and 0 carbonate in that water to start with. Now that's probably not strictly true. There's probably a small amount of each of those species in the water. But for this problem, it's a good enough assumption. And for most of these problems that I give you, or really all of these problems that I give you, if I don't state that an ion is in the solution, you can just assume that it is not. Okay, so for these species, they have a starting concentration of 0. And for calcium carbonate, since it's a solid, we're just going to say it's present. We actually don't know how much is in there. and we just know a small piece of chalk fell into the water. I don't actually give you the grams of this or the volume of it or the number of moles or anything. So we're just going to say it's present. Now we need to figure out how much these concentrations change as this calcium carbonate dissolves to become carbonate, or the calcium ion and the carbonate ion. Well, the calcium, we are going to say, is going to change by an amount of -x. That means that it is being lost as calcium and carbonate are being formed. So how much is it lost? Well, we don't know, but we're going to just say it's equal to -x. And then for every mole of this that's dissolved, we know we're getting 1 mole of calcium and 1 mole of carbonate. So they are each changing by +x. And then at equilibrium, we just take this initial line and add this change line to get our equilibrium line. So present minus x is still about present. It's about the same thing. And for calcium, 0 plus x is going to be equal to x. And for carbonate, 0 plus x is also equal to x. So now we know our equilibrium concentrations for calcium and carbonate. We can plug that into our KSP equation. So KSP is equal to x times x, which of course is equal to x squared. That's equal to 3.36 times 10 to the -9th. Now we are looking for x to figure out our concentrations of calcium and carbonate. So we can solve that by just taking the square root of this equation. That'll give us x equal to 5.8 times 10 to the -5th. And this is in molar. So this is what we call our molar solubility. So what does this x actually mean? Well, this means that our concentration of the calcium ion in our water is now 5.8 times 10 to the -5th molar. That's the concentration of our carbonate in this water also. This also tells us how many moles of calcium carbonate are going to dissolve for every liter of water that it's put in. So you'll notice that the molar solubility of calcium carbonate is 5.8 times 10 to the -5th, but the KSP is a value times 10 to the -9th. So the solubility constant and the molar solubility are different values. And you need to understand the difference between those values and how to calculate one from the other. Okay, but our question wasn't just what is the molar solubility constant or the molar solubility or the concentration of calcium. The question is the calcium in our water more or less than how much calcium is in a Centrum vitamin, which contains 200 milligrams of calcium. So let's go from this calcium concentration to the number of grams or milligrams of calcium and compare. All right, so we know that this is in 1 liter of water. So if we take this concentration, we multiply it by 1 liter, then we have it in moles. Now to go from moles to liters, we need to multiply by the molecular weight of the calcium carbonate, and that will get us into grams. So now we have 0.00232 grams of calcium in this water in the form of aqueous ions, but our Centrum value is in milligrams, so let's change this to milligrams by multiplying by 1,000. Now we have 2.32 milligrams in this 1 liter bottle of water. Is this more or less than the 210 milligrams of calcium in that Centrum vitamin? It's way less. So dissolving chalk in water is not the best way to get calcium. If you want calcium, just go take a Centrum vitamin or drink some milk. All right. If you have any questions about this problem, feel free to let me know or throw a question out to the class. A few of you have reached out to me, and I had Zoom meetings with a couple of you. So if any of you are feeling shy about having a Zoom meeting with me or reaching out via email, you shouldn't be. I'm a fairly nice guy. I generally am pretty accommodating with getting back to people and working through problems with people. All right, now we're going to work on another problem. It's very similar. This is called the common ion effect, or that's the principle that this problem is going to cover. All right, so we just saw in the last slide that the molar solubility of calcium carbonate in pure water is 5.8 times 10 to the -5th molar. Now let's figure out what the molar solubility of calcium carbonate is in water that contains 1 × 10⁻⁵ molar sodium carbonate. So again, the solubility constant for calcium carbonate is 3.36 × 10⁻⁹. Now I've already written some of this problem out. We still have the same reaction here where calcium carbonate is going into water, forming the calcium ion and the carbonate ion. And we still have the same equation for KSP, where we have 3.36 × 10⁻⁹ equal to the concentration of calcium and carbonate ions. And of course, here we're still going to do an ice table. So what is the big difference between this problem and the previous problem? Well, it is this. If I fill out my ice table, you'll notice that the initial values for calcium carbonate are still present. The initial value for calcium is still 0. But for carbonate now, we have to include the concentration resulting from adding this sodium carbonate. So the sodium carbonate was added at a concentration of 1 × 10⁻⁵ molar. And for every mole of sodium carbonate we add, that's going to dissolve to give us 1 mole of bicarbonate ion. So the concentration of the carbonate ion is equal to the initial concentration of sodium carbonate. Okay, now for the change, the calcium carbonate is still going to change by -x and have an equilibrium value of present. And the calcium is still going to change by +x and have an equilibrium concentration of x. But for carbonate, it is going to change by +x and have an equilibrium concentration of 1 × 10⁻⁵ plus x. So now we'll plug all that into our KSP equation. And now we have x times this value plus x. So when we multiply that through, we're going to get x² plus 1 × 10⁻⁵ times x equal to 3.36 × 10⁻⁹. So we have an x² here, we have an x to the first power. How do we solve this now for x? Well, what we're going to have to do is convert this into an equation like this, where we've solved for 0 now. So basically we've subtracted this value for KSP over onto the left here. And now we have something that looks like ax² plus bx plus c equal to 0. And we're going to use what's called the quadratic equation. So a lot of you have seen this in the past. And we are going to solve for this guy. Now, if you'll remember in the quadratic equation, it looks like this: x equals -b. And normally it's a plus minus here, the square root. So it's -b plus or minus the square root of b² minus 4ac divided by 2a, where the a term is the value that's in front of x². The b term here is the value that's in front of x. So in this case, it's 1 × 10⁻⁵. And our c term is this value at the back. So it's -3.36 × 10⁻⁹. But in the normal quadratic equation, you get a plus or minus value here. But for these common ion effects, or for all of these KSP problems, you always have a -b here. And in this equation, b actually always works out to be positive. So you get a -b, and your x value needs to be positive. And your square root of anything always has to be positive. And so the plus minus actually works out to where we always only care about the plus side of that. Now, if you didn't follow the logic on what I just said, that's fine. Just know that for this equation, you're going to use this equation, and you're always going to be using the plus version, not the minus. And that'll save you a step. So then we work through this, and we solve it to get a value of 5.32 × 10⁻⁵ for our molar solubility. Now we compare this value of 5.32 to this value of 5.8. So these are both molar solubilities of calcium carbonate. But why are we getting a lower molar solubility than what we got in pure water? Well, the reason is because now we're not dropping it into pure water. We're dropping it into water with sodium carbonate. And that sodium carbonate is adding carbonate to the water. And this is just an application of Le Chatelier's principle, where we've added some carbonate to this solution. And because we've added carbonate on the right, we're shifting our equilibrium to the left.